All right, welcome everybody. This is CO2 Research Center talk from CO2 Research Center. So we have this monthly lecture series supported by Novo Nordisk Foundation. And today we have to have some advertisement one more time that this is a monthly lecture series, but you have to sign up every time right now with the technical issues. That means that you have to go to the CORC Research Center website, which is corc.au.dk, and you can find the link very easily to sign up here. Can also find all the research talk series speakers, previous and planned speakers for the next month coming. And today we have very exciting speakers, Jeffrey Reimer from UC Berkeley, and Arun, internal speaker from the CO2 Research Center from Stanford. And we will start with Arun's talk today. And let me introduce Arun while Arun can put up the slide. I will stop the slide here. Hi, Arun. Yeah. So Arun studied in IIT Bombay to obtain bachelor degree in mechanical engineering and obtained PhD in UC Berkeley in 1989. He stayed in other institutions, but came to UC Berkeley as a professor in mechanical engineering, material science, and engineer, and then took a position in the more governmental section in Obama administration. Basically served the country as a senior advisor to the Secretary of Energy and also founding director of the ARPA-E program during this time. And then he was, after the government job in the Department of Energy, he took the position as a vice president at Google, and then moved to Stanford as a professor, faculty member. And right now he just positioned in a very with a big announcement as an inaugural dean of the Stanford Doerr School of Sustainability. Of course, he has many membership and positions, but one of them is the senior fellow at the Hoover Institute, a think tank. And of course, another thing to add is that Arun is a main PI of the CO2 Research Center that currently as a main researcher in tackling various problems. And today, Arun will talk about how we can mitigate the global issues based on our fundamental research in terms of scale, what matters with the scale. And hopefully we can learn and discuss many things. Arun, please take over the stage, and thank you very much for accepting this invitation, although your hectic and busy time. Thank you very much.
Thank you, Juwon, for the kind introduction. I'll get right into it. The title of the talk is "How Can Our Research Have Gigaton Scale Impact?" And I think we all want to see this happen because it is a massive problem that we are facing. This is a report from the National Academies, and there's some papers associated as to what do we need to do to keep the global average temperature rise below 2 degrees. And on the vertical axis is gigatons of CO2 per year. And the yellow line on top out here is business as usual. And this is the target of below 2 degrees Celsius. And as you can see, we have to do at least 2 things, if not more. One is mitigate on tens of gigatons of CO2 emissions. And there's this blue region out here of negative emissions on the order of 10 gigatons of CO2 per year, growing over time. And unless we do both, it'll be very hard to keep the global average temperature rise below 2 degrees Celsius. Now, we throw gigatons very loosely, but it's important to understand what that scale really means. And some of you have seen me use this analogy that what is the total weight of all 8 billion human beings on Earth. And you can do your calculation, turns out to be half a gigaton. So we're talking about tens of gigatons per year. So you can see that this is an enormous scale. And if you ask the question, how many industries are already at the gigaton scale, you're thinking about oil and gas, cement, steel, agriculture, water, etc. So if you are to do negative emissions at that scale, you have to imagine an industry at that scale to be able to do what we are trying to do in removing CO2 at the gigaton scale from the atmosphere. There's a report that I co-led for the US Secretary of Energy, Ernie Moniz. This is a CO2 task force report where we laid out what is required for negative emissions and CO2 utilization. What is the landscape like? And you can do various capture sources, capture and conversion, capture products, all the way to the end states, and sort of feed back into the CO2 emissions again. And as you can see, this is a very complex landscape. There are many options and multiple pathways, and it is not just science and engineering. It's science, engineering, economics, scale, finance, markets, regulations, and all of the above. And they all interplay with each other if you're thinking at that scale. So what matters at scale, just to start with, again, scale, the rate of removal is very important, not just the scale, the cost and the price on CO2, which is a policy measure. The amount of energy that you need is going to be in the exajoule scale. The financing will be hundreds of billions of dollars a year, talking about infrastructure, regulatory approvals, all the way to really looking at unintended consequences of what you do, and finally public acceptance. Without public acceptance, none of this is actually going to move. So this is, sounds very daunting. So how do we then, when we are doing research, how do we look at negative emissions? And I see two approaches. One is you start small in the lab and then try to scale up with all of those considerations in mind. And the other is altering processes already occurring at the large scale, and the alteration is what you do in the lab. And so I'll give you two examples of how these two approaches can be done, and may set some goals for the CO2 Research Center of how to approach these problems. Let me first talk about the start small and then scale up. This is what we often do. You have a chemical direct air capture, you have sorbents, and CO2 is absorbed from a dilute mixture, and then you need some energy to dissolve the CO2 in a concentrated form, and we can do research on the sorbents, but you also have to do research on the plants to make it more efficient. And this is what has led to what we have today, whether it's high temperature process using carbonates, which happens at about 800, 900 degrees Celsius, or you can do low temperature processes using amines and other means, which is, in the 120, 100 degrees Celsius, and hopefully lower and lower temperature. Now, this is what we are doing today. There are lots of small companies that are starting up in this area of direct air capture. But it's important to understand what the energetics are. And if you look at the energetics today, and this is improving, but typically today we need about 2,000 to 2,500 kilowatt hours per ton of CO2 of energy that is required. And most of it is actually heat, is the energy required to dissolve the CO2. And so if you take this number, let's take 2,500 kilowatt hours per ton of CO2. 1 gigaton of CO2 will require 2,500 terawatt hours of GHG-free, CO2-free, and other emissions-free energy. Just as a reference point, the 2020 US production of carbon-free electricity from nuclear, wind, solar, hydro is about 1,500 terawatt hours. So we will need a lot of energy if you are to go along today's approach, today's technology. Clearly, we have to improve it. And so how far can we improve? Well, the thermodynamic limit I mean, depends on how you calculate, it's roughly around 100 to 125, kilowatt hours per ton of CO2, which is 20x lower. And you don't want to be at the thermodynamic limit because then nothing moves. There are no rates. So ideally, in engineered systems, you want to be about 4 to 5x of the thermodynamic limit. So there you have some rates. And that is on the order of 400 to 500 kilowatt hours per ton of CO2. And if you can get that, then the energy demand that you would need is much lower. And frankly, you would then be, it's a much easier approach to this. The question is, how do we get there? And of course, if you can do the energy reduction, the cost of carbon capture comes down. And it really turns out, and this is where I think some of our research can go into, it really goes into the sorbent. And this is, I was involved in another report, which is the American Physical Society report, the first actual report on direct air capture, where we laid out where are the sorbents today. And the vertical axis is kinetics, it's a rate constant. On the x-axis is the heat of reaction, which is kinetics and thermodynamics. And it's important to point this out that the current materials, whether it's MEA, monoethanol amine, or OH radicals, which is used for carbonated formation, kind of fall in one line. And there's a penalty that you pay for where you are on this chart. The heat of reaction is what the energy that you need to break the CO2 bond from the sorbent. And that is your operating cost. I mean, these kinetics and thermodynamics directly related to cost. Because you have to add more energy to remove CO2, that changes your operating cost. So the farther you go on the right-hand side, the more operating cost you have. And if you have low kinetics, that means the rates are small. That means you need a larger sorbent in a surface that you to bind to. It changes your capital cost. So lower selectivity and capital costs, you go down this way. And ideally, your sorbent needs to be out here. And we are trying to find whether MOFs or something else are in this region. The MOFs are fantastic. They need to be stable, but that's the direction we need to go to really find ideal materials that are moderate heat of reaction, and so moderate operating costs, and also high rates, and so that you reduce capital costs. So that is a research target that we should be looking at. This is on the chemistry side, and I'm sure Jeff could talk about that as well. But it is also not the chemistry that is the only thing important. You have to look at the reactor design and everything. So the last point, design, build, and demonstrate scalable reactor design that offer the possibility to substantially reduce carbon capture and separation costs is as important as the sorbents itself. So this is a way, going back to starting small in the lab, trying to find the sorbents, and then scaling up from reactor and all the other things that are required. Let me give you an example of the other approach, that is alter processes already occurring at large scale. And I'll put three comments out here. One is CO2 is dispersed at an average of 420 ppm. That we know. Any separation or conversion that we need of CO2 needs energy. Unless you have a downhill reaction like a carbonate reaction, but then you have to then remove the CO2 from the carbonate. So any separation would need energy. So if CO2 is dispersed at 420 ppm, we will need some dispersed form of energy. That dispersed form of energy is sunlight. And so there's a lot of discussion, of course, in photosynthesis for biofuels, but I would actually go and look at it from a negative emissions point of view. Why do I say that? It is because the global crop residue, crop is of course used for food and is grown annually, and only less than 10% of the crop is actually food. The rest 90% is absorbed CO2 from the atmosphere, and the global crop residue remove roughly 10 gigatons of CO2 from the atmosphere annually. This is already at scale, and we don't quite think of it as a negative emissions play. In many parts of the world, they're burnt away. So while agriculture, I think, is carbon engineering 1.0, We need a carbon engineering 2.0 to remove CO2 from the atmosphere. So this is just one option of photosynthetic. This is using, of course, Kelvin-Benson cycle. There are many other cycles to fix CO2 with organisms, and we should look at photoactivated approaches to fix CO2 in using organisms. In this case, it is, for instance, photosynthetic mechanism. Why do I say this is important? Because if you look at the global crop residues, 75% of it is cereals, barley, corn, wheat, and rice that is grown around the world. Sugarcane is about 10%. Then there are legumes like soybeans and tubers, etc. And as I said, the global crop residue is on the order of about more than 5 gigatons of mass crop residues, and the atmospheric uptake is about 10 gigatons of CO2. The cost of biomass is about $60 per dry ton. And if you take that in equivalent on CO2 capture, the cost of CO2 capture is about $33 a ton of CO2. And so the carbon value, we have always been thinking of the cellulosic and lignin biomass as a source of fuel. I would rather actually now think about that as a source of carbon, negative carbon. And the carbon value of crop residue is more than its actual fuel value, and depends on the price of oil in the market. So one approach to think about is, can we find a low-cost approach to make the biomass inert against biodegradation, so that methane and CO2 are not produced by biodegradation, and then recarbonize the soil, put it back in the soil so that all the minerals and other phosphates and all actually go back into the soil and thereby recarbonize the soil, which is good for agriculture anyway. That is something, and it has to be a very low-cost way to make the crop residues inert. So this is an approach. So again, going back to this, what I talked about is a different approach, things that are already happening at large scale for CO2 negative emissions, but tweaking it, altering it to get to negative emissions, what we want. Let me end my talk very briefly with removing atmospheric methane. And I'll give you another example of this, because I think this is one of the most important problems we can solve. Why? Because methane emissions, the concentration is going up. It's almost about 2 ppm. Methane is extremely inert, it's symmetric, and the global warming potential is high, as is shown on the right-hand side. The radiative forcing from methane is about half or more than half of CO2. And while you can remove CO2 from the atmosphere by photosynthesis, that's where you get the oscillations in the Keeling curve, it is very hard to remove methane. And so this is, many feel, this is the sleeping giant. So what can we do with it? So these are the sources of methane. As you can see, these are from fossil fuel production, from agricultural waste, biomass, biofuel burning, wetlands, and things like rice. If you grow rice, you get a lot of CO2 emissions. Cows produce methane, and so agriculture is a big source of methane. But there's a sink of methane, which is a natural process, which is out here. And that is, the question is, how does the atmosphere remove methane from the atmosphere? I won't go into too much detail. These are the sources of methane, but I just focus on one. These are emissions. This is qualitative. There is no data yet, and this is in ppm. So landfill, you get most of the concentration of methane around roughly about 100 ppm or so. If you're doing enteric, which is cows, that's on the order of 1500 ppm. But if you're looking at coal mine methane, it's on the order of a few thousand ppm. Now, it turns out that it is very difficult to do catalytic combustion of methane, anything below 1000 to 2000 ppm. So the question is, how do you remove then when you're at 2 ppm? As I said, I mean, this is extremely hard, very hard to activate methane. One of the CH1 activation, one of the hardest problems in chemistry. You can do it catalytically. You need about 800, 900 degrees Celsius to do that. Matteo and I are actually working on that right now for methane pyrolysis. But it requires high temperature. So it's very hard to think about heating up the atmosphere to actually do this. We need a room temperature process. What is the room temperature? What's the natural process? It's by OH radical chemistry. And the way it works is, and this is understood to some extent, but the details are not completely understood. You have UV photons that activate ozone to produce oxygen and oxygen atom. Oxygen atoms react with water to form OH radicals. And the OH radicals at room temperature can activate methane to form methyl radicals in water. And the methyl radicals then becomes an active species that can go down to formaldehyde or CO2, etc. But there are competition. If there's CO in the atmosphere from burning fossil fuels, partial burning fossil fuel, they can remove the OH radicals. They react much faster, and thereby, become a competitive process. And of course, you can hydrogen atoms can react with oxygen to form OOH, hydrogen peroxide radical. And there's a very complex interaction with NO that can produce more radicals, but it's a complicated reaction. I won't go into the details. The concentration of OH radicals is about 10⁶ centimeter cube. Lifetime is roughly around 1 second, but the details of the reaction are not completely understood. There's some, and I'll just give you, there's some very interesting results that are coming out recently from China, where they are looking at taking that process and trying to replicate that in the lab. They've with semiconductor photoactivation, zinc oxide silver, in this case copper oxide zinc oxide, where they have been able to get down to about 100 ppm of photoactivation to remove it. And these are some of the results that have been produced. We are also looking at this in our lab using titania with some catalyst, and we can activate methane, and we can get all kinds of things like methanol, and we can tweak the reaction in different direction, and we can certainly produce CO2 if you really wanted to. So this is going on as we speak, and we're trying to get down to 100 and hopefully below 100 ppm so that we can replicate what is there in the atmospheric chemistry. Again, let me end with this. How can our research have gigaton scale impact? And I see really two approaches. One is start small and then scale up. And that we are looking at the sorbent kind of approach. And the other, and I give two examples, altering natural processes already occurring at larger scale, and then working on the problem in the lab that can replicate and then amplify what is already going on in nature. Let me stop here. Thank you so much, Ivo.
Thank you very much, Arun, for this clear talk about actually depressing topic. But I think after listening to you every time, I think it's the topic becomes more optimistic. So I would like to see if there's any questions, Q&A section. Maybe I can start some questions. So you mentioned this agricultural process and the methane radical, let's say, CH activation as a tool to use the big scale and then utilize that and altering those processes to mediate this CO2 or let's say greenhouse gases. But the methane activation, how can we alter in a global scale if you can deploy maybe those catalysts in a gas phase? That was something I was wondering.
Yeah, so good question. We are nowhere close to that, but let us say either our or someone else's research is wildly successful in the lab, where you could take the UV concentration that is available in nature in terms of fluxes, UV fluxes, and excite a semiconductor metal, sort of catalyst that can absorb the natural UV light and activate methane, either using OH radicals or directly. You need a competitive reaction with, or for the electron acceptor, you need oxygen.
Yeah.
And oxygen is there in the atmosphere. And let's say you were able to do this in atmospheric conditions, and you're down to 2 ppm or below 2 ppm.
Yeah.
Now that would be an ideal scenario, because then you can think about how to deploy it, whether you add it to a direct air capture for CO2, you add this on, it's an add-on. So you're processing CO2 or methane simultaneously.
Yeah.
Or you could, think about, and these are controversial issues of solar geoengineering, where you disperse particles of titanium. The titanium is inert. So you disperse particles of titania, and thereby, and so that after a while it settles down. There have been lots of proposals for reflecting sunlight with this, which is great. It gives you some breathing room, but it really doesn't solve the CO2 or methane problem. This one could actually remove the methane and form formaldehyde or CO2 or so. So I think that those are the approaches, but that will come at scale, and that will require public acceptance, policy measures, and things like that when it comes to scale, right?
Yeah.
Or you could paint buildings. I mean, there are buildings in Japan that are painted with titania on board, which are so that your moss and other green stuff doesn't accumulate when you have it's basically a detergent, photoactivated detergent.
Wow, thanks. I think Jeff has a question. I think maybe you can unmute and then does it work?
Yeah, thank you, Arun. Lovely and compelling talk. Brief question: to what extent do you think it's important to deploy methane measurement to look at sources and maybe focus mitigation at sources?
Huge, very important. So right now, as we speak, there are airborne as well as satellite measurements that are going on. New satellites are being launched right now for these measurements, and you need a combination of both ground-based, airborne, and satellite measurements to really accurately find out how much methane is being emitted by natural gas supply chain. And what we are finding, one of my colleagues at Stanford, Adam Brandt, has just published a paper that in the Permian Basin, when you're doing shale gas, 9% of the production volume is leaking. And as we know, anything above 3 or 4% methane is worse than coal. So this is really bad. There was a paper in Science that came out from a Tropomi, which is a European satellite that measured massive amounts of methane coming out in Russian and I think Turkmenistan and others. So this is really bad. And this is not even counting. So there are satellites, EDF is putting up a satellite, and this is not even looking at the permafrost that is warming up and maybe producing methane. We don't know yet, frankly.
Yeah, we have some questions from the audience. So continuing with the methane mitigation, if this solution that you suggested, should it work only with a stream of methane, like a high concentration or low concentration of methane? Also, what about the risk? I think this is related to the comments you already made, Arun, about the risk of the contaminating the atmosphere.
Right. I mean, these are very important issues. I think anything we do at the gigaton scale has risk involved.
Yeah.
And there are unintended consequences that we have to think about. There is absolutely no question about that. Frankly, I mean, as a practical matter, it may be better to not do the atmospheric one right away, but rather look at agricultural methane, like in a big barn where there are lots of cows, put a vent out there with a fan, and then remove the methane from that so that methane doesn't go out there.
Yeah.
Or take coal bed methane and remove and do the processing locally, as opposed to the 2 ppm, which is obviously much harder to do. So that would be my first, and then try out and get some global consensus. So if methane really becomes a problem, whether some controlled experiments in the atmosphere might be doable or not. But these are controversial issues.
Yeah, yeah. Another question, continuing with this gigaton scale mitigation. So with the agricultural carbon, let's say, sequestration, what kind of options do you think we have to move this residues into soils and then increase the residential time of those carbon, let's say carbon zero in soil?
Yeah, I mean, that's a good question. That's part of the reason I kind of said that we need to process that biomass a little bit to make it as inert as possible to all the organisms, so that the organisms then don't eat the the biomass, and then produce CO2 and methane. That would not solve the problem. So what kind of, so there are all processes like torrefaction to make biochar and all. Those require 300, 400 degrees Celsius. That becomes a, that's energy intense then. The question is, can you do something? And this is a research question. Can you do something at biomass at low temperature, low energy required, low cost to make it inert enough and thereby be amenable to recarbonizing soil without the CO2 and methane impacts?
Mm.
That would be terrific.
We just got another question. So to what extent the minerals or metal ions in the soil can impact actually the methane, let's say, actually I think it means CO2 sequestration, so carbon sequestration. So I guess it's about oil chemistry, yeah.
So there was a paper that came out in, I believe, Nature, where they said, okay, if you were to take CO2 from the atmosphere, you can put some alkaline rocks into crops, into the soil, and let that absorb the CO2. And of course, this can be done. I mean, we know that to form carbonates. It'll be a slow reaction, but nevertheless, it will happen over time. This is how CO2 has been removed from the atmosphere in the past when you have alkaline rocks exposed by volcanics, eruptions and things like that. And the cost is roughly around $100 a ton. And I think it's important to consider that. I think that's certainly an option. But then you also have to use the supply chain then of taking basalt from the ground, crushing it into smaller pieces, and then distributing. And they have to ask the question, okay, will the farmers agree to do that? And are there benefits and co-benefits and all that? So yes, it's a downhill carbonate reaction. Everyone knows this will work over time.
Yeah, I think we will have more questions, but for the time constraint, I think we should wrap up the discussion here. Thanks for the questions from the audience, Lars and Lisa and Trisha. And